In this video, we are going to look into free fall. Free fall is motion under the gravity when there is no air resistance. Near Earth's surface, all free falling objects have the same acceleration, regardless of their mass. The magnitude of this acceleration is 9.80 meters per second square. If we choose the upward direction as positive, then the acceleration will be negative 9.8 meters per second square. The hammer and feather examples show that without air resistance, objects fall with the same acceleration. On Earth, air resistance can affect motion, but in ideal free fall, we ignore air resistance. This lets us use the same kinematic equations with acceleration equals to negative g when we consider the upward direction as positive. Free fall is vertical motion, so we use the variable y instead of x to indicate the position. We will be using the same kinematic equations as we did before, but now acceleration is negative g, since we select the upward as positive. Remember, when we select the positive direction, we follow the sign convention in Cartesian coordinate system. So for a vertical motion, we pick upward as the positive direction by default. So our main three kinematic equations will be taking the form as shown below. Now let's look at an example. A person standing on the edge of a high cliff throws a rock straight up with an initial velocity of 13 meters per second. The rock misses the edge of the cliff as it falls back to Earth. Calculate the position and velocity of the rock at 2 seconds after it is thrown, neglecting the effect of air resistance. When you solve a problem like this, it is easier if you create a rough diagram. So let's draw a cliff like this, and the stone is thrown from the cliff up and it goes up, comes down, and the initial velocity here is, let's say, v naught. And the next step is writing down all the given variables or the known values. So initial velocity v naught is 13 meters per second. Acceleration is negative g. Time is 2 seconds. And also we can consider the initial y position as 0. Now the question asks us to find the final y position at 2 seconds. So to do this, we have to select a kinematic equation from our list. So if you look at the list here, in the first equation, we do not have position, so we can't use it. In the third equation, time is not there, so and also we don't know the final velocity, so we can't use the third equation as well. So we have to go with this second equation. So let's use it. Y equals y naught plus v naught t minus half gt squared. Alright, so let's substitute the values. Y naught is 0. V naught is 13 meters per second, and times t is 2 seconds minus half g is 9.8 meters per second square times 2 seconds squared. Now notice here, when you substitute for g, we substitute a positive value. We substituted positive 9.8 because when we write down these kinematic equations, we already considered the direction. So we already considered that we are considering upward as positive and g is a negative value. So if you put another negative sign when you do this problem, it will be wrong. So be careful with the sign when you work out these problems. Now the answer here is 6.4 meters. And for part B, we have to find the final velocity. And for that, we can use this first equation because we know the initial velocity, we know the acceleration, we know the time. So we can use the first equation. V equals V naught minus gt. So let's substitute the values. So V naught is 13 meters per second minus g is 9.8 meters per second square times t is 2 seconds. And this is equals to negative 6.6 meters per second. So what that means is when you throw the stone up, goes up, go all the way up and comes down. So when you get a negative value for the final velocity, it means the stone is on the way down because the velocity is negative means it's downward. And since we got our final y position a positive value 6.4 meters, it means this is right now situated above the starting point. So this distance will be 6.4 meters, and then the velocity at this point is 6.6 meters per second pointing down. Let's look at another example. The referee tosses the coin up with an initial speed of 5 meters per second. In the absence of air resistance, how high does the coin go above its point of release? Now here we have a picture given. So the initial velocity is 5 meters per second. And when you toss the coin up, it goes up and comes to a stop when it reaches the maximum height. So final velocity is equals to 0. Now let's see how we solve the problem. The first step is writing down the known values. Initial velocity is 5 meters per second. Acceleration is negative g. The initial y position, we can consider it as 0. And the final velocity is also equals to 0 because we are considering the maximum height of this motion. Now we have to select the appropriate kinematic equation for this problem. The first two equations can't be used because we have time. So we don't know the time and we don't have to find the time, so we don't need to use these two equations. So let's look at the third equation. We know the final velocity, we know the initial velocity, we know the acceleration, and we also know the initial y position. So we can use this equation to solve the problem. So let's use it. V square equals P naught square minus 2g times y minus y naught. And let's rearrange this. Let's bring this v to this side and bring this to this side. So we have 2g y minus y naught equals to v naught square minus v square. Now let's divide both sides by 2g. So we get y minus y naught equals v naught square minus v square divided by 2g. So let's substitute the values. So y minus 0 equals 5 meters per second square minus 0 divided by 2 times 9.8 meters per second square. Again, when you substitute for g here, we consider the positive value because we already considered the negative sign when we consider this kinematic equation. So the final answer here is 1.28 meters.